Today we're going to review a couple of theorems from our similar triangles unit. And the first one's called the side splitter theorem. And what that's all about is if I have a triangle and I have a line segment that connects two sides of the triangle, and if that segment is parallel with one of the sides, so DE is parallel to AB, I can mark it like that, then the side segments are going to be divided up proportionally. And we can say that DC over DA is equal to CE over EB. So the two sides are proportional. Now, to show you that, here's an example. AC is 9, DC is 6, CB is 12, and we want to find CE. So for this first example, I have the entire side length is 9, and DC is 6. CB, that entire side length, is 12. And I'm trying to find CE. Well, you can just see from the diagram how to set up the proportion, because you have the top to the whole side equal to the top to the whole side. So this is fairly straightforward. We can say 6 over 9 is equal to x over 12. So 9 times x is equal to 12 times 6, which means 9x is 72, and CE, which is x, is going to have a value of 8. So the side splitter theorem, when the sides of a triangle are split and that splitter is parallel with the bottom side, or with the opposite, the third side, then the sides are divided proportionally. You can do top to whole, or you could do top to bottom. That would also work. But let's take a look at this second example. We have CE is 6, and EB is 3. DE is 10, and I want to find AB. The rules are different when you're dealing with the parallel sides. You have to be careful, because if you look at this, I have a small triangle, triangle CDE, and I have a big triangle, triangle CAB. Those are the two things that you can compare. You cannot compare these bottom segments with anything because they aren't a side of a triangle. So you can't do that when you're dealing with the parallel sides. The correct thing to do here is to find the entire side length of the big triangle CB. 6 and 3, that's 9. So now we can set up our proportion. AB over DE is going to be CB over CE. I cannot use that bottom segment. I can use the top segment because he's a complete side of the small triangle. So big to little, big to little. So here's how it works. X over 10 is equal to 9 over 6. So 6x is equal to 90. And x is going to be whatever I get when I divide 90 by 6. That's going to be 15. So you have to be careful. You have to see what you are given and what you are trying to find. If it's the parallel sides, you have to do whole to whole. You can't do the little segment down here by itself. So now we're going to try one that's a little more complicated algebraically. We're going to label all of our items here. We're always given that these are parallel. So labeling, I have AD is x, and CE is x. DC is 1, and EB is x plus 2. So, in this case, I'm not dealing with the parallel signs. Therefore, or the parallel sides. Therefore, I can set up a proportion with the segments. It's okay at this point because I'm not dealing with the parallel sides. So when I do that, I have 1 over x is equal to x over x plus 2, because that's DC over AD equal to CE over EB. Well, I cross multiply like I always do. X plus 2 is equal to x squared. This is a second degree equation because I have an exponent here of second degree. Because of that, I need to put it in standard form. I've got to set one side equal to 0 and keep my squared term positive. And then I have to factor to solve it. Anytime you have a second degree, more or less in here, we're going to factor to solve it. My 2 has to be negative, my 1 has to be positive to get that negative 1 in the middle. And then I set each factor equal to 0, and I got to move up here because I'm running out of room. I get x is equal to 2, and x is equal to negative 1. Well, this is a problem where we're dealing with side links, so I can't use the negative 1 value, and I have x is 2. So in this case, I know that AD is equal to CE, which is 2, and EB is going to be 2 plus the 2, because there's my algebraic expression, so EB is going to be 4. The second concept we're going to talk about today and review is the concept of having proportions in right triangles. Here I have triangle ABC, the big triangle, and it's a right triangle. And this is an altitude drawn from the right angle in this triangle. Well, that creates a couple of segments that we call mean proportionals. And the mean proportional is the value that I can put in twice. Typically it's lower left, upper right. And everything else you would put in two other numbers, A and B, and you would cross multiply and solve. So our goal is to identify what is going to be the mean proportional, and then the other two segments are just put in its place. But this is the key here. Well, there are two setups. The first one is the hypotenuse AB. AB over one of its legs is equal to that leg over the projection. The projection would be the shadow, so it's half of the big hypotenuse, or one side of the big hypotenuse that's under the leg you're talking about. So what this means is, in a right triangle, the leg is the mean proportional between the hypotenuse and its projection. So in letters, the hypotenuse is AB. I'm always referring to the big right triangle. So that's the hypotenuse over AC, that's the leg, and AC is the mean proportional, so he's written twice, and the projection is AD. Or, on the other side, AB over CB is equal to CB over DB. So the second setup is dealing with the altitude. The altitude is the mean proportional between the hypotenuse segments. So the altitude splits that hypotenuse up into two segments, and it is the mean proportional between them. So hypotenuse, the altitude is the mean proportional. So in letters, that would be the hypotenuse segment, AD, over CD, and CD is written twice because it's the altitude, and that's over DB. The altitude is the mean proportional between the hypotenuse segments. So now we're going to work a couple of examples, and we choose which mean proportional we're going to use based on what's given and what we're trying to find. So in this first example, I'm given that DB is 8, and AB, the entire hypotenuse, is 18. And I want to find CB. So that's the proportional. That's hypotenuse, leg, leg, projection. So the leg is the mean proportional. If we're going to do that, in letters first, it's hypotenuse, leg is equal to leg over hypotenuse segment, DB, or projection. Hypotenuse, leg, leg, projection. So now we'll put in our numerical values. The hypotenuse was 18. The leg is what we're trying to find, So I have an x in two places, and the projection is 8. Cross multiplying, I have x squared is equal to 144. Taking the square root of x squared is equal to the square root of 144, and I get a value of 12. So that answer comes out to be 12. So now looking at the next example, I have BD is 19, AD is 10, and this time I'm trying to find CD. So this is an example where the altitude is involved. The altitude is the mean proportional between the hypotenuse segments. So I know in this case that my altitude is the mean proportional. It is not always the case that the altitude will be that, but in this case it is. And we'll work more examples in class where you'll see the difference. And the other two values go above and below. Cross multiplying, I have x squared is equal to 190. And 190 is not a perfect square. So if we're going to round to the nearest decimal, let me see what that is. That's going to be x. We got to take the square root of 190, and in this case we're going to round to let's say 1 decimal place. So x is going to be approximately equal to 13.8. Now there'll be other cases where the mean proportional is not what you're looking for, but the setup is the same. So if you have an altitude, the altitude is going to go in the mean proportional space, and the hypotenuse segments will go in the other places. And then it's always an issue of cross-multiplying and solving. So we will work more of those examples in class tomorrow.